Thanks for coming. I'd like to thank the organisers for putting this together. Thanks, Carmen. It's been a huge headache, I imagine. I'm Richard. I'm here representing Open Free Energy, which is one of the many OMSF projects. So quick outline for my talk will be roughly chronological. So how did we get here? What are we currently doing? I'm going to dive into a bit of the just what we've done, but also the how and the why we did it that way. Then a bit of sort of future tense. What are we doing next? Where are we going? What do we hope to do? And then also that's going to be informed by this sort of last point, which is what's planned for the rest of the event. It's a rough outline for what we're doing today. So a bit of history. 20 years ago, I think at the last meeting in Göttingen, there was this document that came out of that, which is the need for an open free energy consortium, which is, I guess, where the rough skeleton of what this open free energy project is was sort of sketched out by various industrial partners and academic partners sort of sat around the table and tried to figure out something they could all agree upon. I think this somewhat led to the creation of OMSF, because this was sort of once you had two projects, you used some sort of projects to hold two projects. So that would be the catalyst, sort of bringing Open Force Field out of Virginia Tech and forming this non-profit OMSF. And this sort of led to this Exhibit C document, which is the sort of the scope of work for Open Free Energy. So that's sort of a rough bit of history about how we arrived here. I'm going to sort of talk quickly about sort of the project structure, because I think it's a little different to Open Force Field, and you might not be familiar with that either. So sort of up top in this factory here, I'm assuming this is what your workplaces look like if you work in industry. They pay funds to the non-profit that's Open Electric Software Foundation, who in turn employ various teams of software scientists, including the Open Free Energy team. These industry folk, along with this industry folk, then direct the Open Free Energy team as to what they should build. There is also a group of academic partners who are the Technical Advisory Committee, the TAC, who along with the industry folk kind of advise on the methods that should be used to achieve the goals which have been directed by the industry teams. It's slightly different between direct and advice there. I'm trying to draw a distinction. We then produce some sort of software, and then that sort of goes back to the industry folk and the academic folk. So this is sort of the cycle we're operating in. So we have our own sort of design, build, test, learn cycle going on. So very familiar. I think we're sort of got around this cycle once or twice with a few people so far. It's sort of the current status of the project. So we're starting to sort of finally close this cycle. I think Joe's giving a talk later about sort of this learn part of the cycle. And I'm looking forward to that because I've not seen it yet, so that'll be fun. So this is sort of how the project's structured and how we operate. Moving on to the team, who are we? So I'm Richard in the top left. I think David and Erfan are both in the audience over here, and Dan's sorry as well. Mike is our designated survivor. He's at a safe location. I can't tell you where. I've been told to point out that both Erfan, Ben, and Mike are all actually on 50% time. We've got a new scientist joining us who is a mystery. And we also got a project manager coming on in June, who's split with Open Force Field because we coordinate quite closely with them. So this is the team. Come say hi. Something that the team has quite a good long history, and we've got quite a varied background, all of us, but we're all quite strong in our sort of open source foundations. So when the team was put together last year, we had a quick chat about how we'd like to do our work and sort of how we want to proceed, and we sort of came up with this list of priorities from sort of top to bottom, which may seem a bit backwards at first. So we firstly want to sort of start up picking up on the maintenance of community packages. We're going to try. We've challenged ourselves to try and be good open source citizens. So this is to sort of push fixes upstream wherever we can, engage with the existing projects wherever we can, and sort of try and improve the field as a whole, rather than just sort of working on our own projects, which is more challenging than sort of doing it the easy way. So only as a third priority are we sort of developing new packages where we're identifying holes in the field. Louder, okay. And then finally, we're then sort of bring this all together into a unified toolkit for free energy calculation. So this is the priority, but we think it should sort of come from the ground up and sort of working on community packages and working on existing things wherever possible. So a lot of the talk I'm giving today is sort of based on sort of what we've done, sort of our packages, but I think I have to acknowledge that we're standing on the shoulders of lots of giants. So we've sort of been working with various other teams, various other projects, some of which are in the room, some aren't. So I just want to sort of acknowledge that a lot of what I'm talking about is our own stuff, but I think there is a background of things which have happened, which have sort of been us contributing to other things and other people helping us out with things. I just wanted to sort of acknowledge that. So the other thing we sort of discussed as a team when we got started was this: how should we be building tools and sort of what sort of tools we will build. I think we kind of arrived on this, adopting this sort of Unix tools philosophy of building tools which do one thing and do it well. It's a bit of a spicy take, but I feel like this Swiss Army knife on the right, it seems like a good idea, but then you sort of think about it, it's not a very good knife, it's not a very good screwdriver, it's not good at any of the things you might think you could use it for, and you're probably better served with a specialized tool for those jobs. So we've tried to also focus on developing smaller packages that do a single thing and do it well. And sort of, in our opinion, at least, these things are easier to debug because there's sort of fewer lines of code. And it has sort of quite tight mode of operations. There's not a lot of room for it to go wrong. Because the code isn't sort of some big overwhelming behemoth, you can attract more contributors that way because it seems like it's more approachable. It has a defined scope. It encourages the creation of alternative components though. If you only have to sort of replace a small subset of functionality, it encourages a lot of innovation. But then obviously eventually you're going to compose that into a larger workflow. So I'm going to start sort of describing various smaller tools that are sort of following this philosophy, but this is sort of a deliberate choice. I think that's quite interesting, and I'll happily talk to people if I'm sort of wrong or right about this. Even louder. Even louder. Okay. So I'm going to sort of try and outline sort of how I think this is sort of worked with a case study of just like Lomap. So Lomap's a tool which originally David Moby created way back in Louisiana for sort of finding these alchemical networks that you want to run free-energy calculations on. So it was sort of, again, it's probably the most widely used tool for this purpose, but sort of is, you think it'd be too big to fail, but when we sort of came across it, it was currently lacking any sense of maintenance, or no one was sort of really looking after it. So we sort of stepped up and assumed maintenance of this. It's doing that, we sort of added this robust set of regression tests to safeguard its sort of behavior. We went through the pain of, you know, updating compatibility with RD kit, providing the content packages people need so they can sort of download and use it. There's a few performance tweaks we did, so it's about 10 to 50 times faster on some sort of networks that you can input. So if you're kind of using an old version, if you update, you might see it produce networks a bit faster. And then finally, we're starting to see sort of new contributors come in and both sort of raise issues with it and also provide fixes. So I think it's sort of starting to live and survive as a open source sort of package in that's living and breathing and is sort of more sustainable and sort of maintainable going forward, which is sort of what we're trying to achieve with these sort of packages. Another thing we did with Lomap was sort of try and break it down and sort of create an API for it, because I think the majority of usage with it would be through a command line utilities, where sort of you put in some files, it produces some output. There's not a lot of room for working with it in the middle there. So we sort of tried to break it down into the various functions it can do. So it does atom mappings, which I think is one problem. It scores those atom mappings, and then it constructs those mappings and networks into a network which has sort of certain properties and certain topologies, and sort of split out all these different functions so that you can use them all independently and sort of get to inspect how each stage of the process is happening as well. So I think this is sort of a better mode of usage for sort of a tool like this. So there's just some quick codes of how that would look and feel. Do you get louder again? Okay. So following sort of feedback from our industry partners about sort of what they are finding when they're sort of doing their work, we identified this need where sometimes atom mapping tools are getting this stereochemistry wrong. So, and stereochemistry is sort of a difficult problem, and I'm not going to say I've solved stereochemistry, but people were complaining that tools like Lomap were getting things wrong. And I think we managed to trace this back to Lomap's based on sort of an MCS, like a 2D approach. And stereochemistry is quite hard in 2D, and it's quite easy in 3D. I'm going to say quite overconfidently. But we kind of came with this Kartograf approach, which is looking at all of the overlap in 3D, because we have these dot ligands which have this 3D information. You can then sort of pair atoms. This will give you like a sparse distance of matrices of sort of sparse matrix of distances about sort of who's close to who, and you can kind of do a linear sum assignment on that sparse matrix to kind of form connections. You can then apply a load of chemistry rules. So the chemistry sort of finally comes in once you've started to assign atom pairs together. These chemistry rules will do things like forbid certain R group transformations. You could stop sort of things like ring breakage or sort of ring size change, sort of known problem cases, and then sort of you get an atom mapping out of that. So this is a new approach which Ben has been working on and gave a poster on the free energy meeting recently. And we've done some very, very preliminary benchmarks, and we're starting to see that it's showing it's definitely not worse than Lomap, and it's starting to show some sort of differences to Lomap, which is interesting. Sometimes better, sometimes worse. And we're also seeing that in some cases it's able to complete transformations and sort of form edges that Lomap fails on. So, which is a bit harder to sort of represent in these metrics here, because it's sort of a failure doesn't appear when you do a comparison. But we're seeing this alternate approach is maybe sometimes solve cases where a MCS-based approach would fall over, which is also quite good, because these things can often fail quite quickly, and so sort of having these two options for how you can do this problem might get you more sort of throughput on your calculations. Okay, so I've been talking a bit about all these sort of like mini packages, but like how do they all sort of come together? How do they all interoperate? And how do they sort of all start to congeal together into a whole? And for this, you need an object model for sort of expressing all the different steps in a free energy calculation, right? So here's the free energy cycle. If you're playing the free energy drinking game, take a shot. But this is sort of defining the building blocks for expressing these various concepts in a free energy calculation. It's not a replacement for things like open force or toolkit or like the RD kit, which is sort of looking at chemical models, because we're expressing all of these sort of individual concepts. So there is the chemical systems, but there's also these mappings in between them. There's the entire chemical systems, but also the components within. And so it's more just a language for expressing these concepts. And so we're calling this Gufe, which is Grand Unified Free Energy. It started off as kind of a joke name, and it's stuck. So I learned a lot about not taking jokey names. Yeah, I guess. So sort of the code of this will look like this, right? So it's using ID kits to sort of hold the chemistry where there is chemistry, but it's giving these like little components which are how people would draw on a whiteboard how they're going to do a free energy calculation. So it's trying to be like a quite intuitive approach to expressing what you're doing with your free energy calculations. So as a way to maybe solidify that a bit more, and sort of why you should care about these sort of object models, if you're just using them, is sort of if you would define how an atom mapping algorithm should behave. So sort of what goes in and what comes out, and sort of sets expectations for how these items should behave and how they should interact with each other. So things like Lomap, things like Kartograf, Ben's work would then sort of fulfill this expectation of behavior. And so then when you have various modules which are sort of fulfilling this behavior, you can then sort of switch between different scientific methods quite seamlessly without having to sort of go relearn how a different tool works, because they're all behaving in a similar way and will react to the same inputs and outputs, or produce certain outputs. So this is why, this is sort of one thing we did, which is to try and allow better interoperability between tools and try and give sort of common language for people to start speaking in. Another thing that all these objects do, and this object model does, is they serialize, which is kind of a boring computer science term. It's actually quite important. Each of these objects, you can kind of save it to disk in sort of in like a binary blob, and it can come back in perfectly the same way. It's kind of boring, but it's actually quite important, because if each of these individual components along the way, you can kind of store them to disk in a file maybe, you can then sort of store them to disk and reload them sort of in a year's time and get the exact same model you just had. You can email them to a colleague. You can kind of attach them in SI. It gives us sort of quite good sharing of provenance of what you did. It's also a key step in looking at when you're trying to distribute work out and sort of work at scale. So David's talk coming up is going to sort of be leading a lot on this idea of can you serialize objects and then sort of start passing them around across a big sort of workflow. And that's sort of another thing this Gufe package gives you that you might struggle with if you were to roll your own, I guess. Cool. Another key concept is this idea of a protocol with a capital P, which is basically you can package up an entire alchemical method into a protocol. And this is sort of a pre-packaged method that people can sort of bring out and run. And this is, you can think of this as maybe like a solver for an edge on an alchemical network. And we're sort of continually testing and validating these as we go. And this is sort of part of the work we do is to show the quality of these. So this sort of code up in the top right is how you would start defining two chemical systems that you wanted to interpolate between alchemically. And then you would sort of create this protocol object, which comes with sort of a default arrangement of settings, which is sort of like a manifold of parameter space in which it'll operate. You can then sort of tweak these a bit if you want to sort of change the temperature, play with the sampling method you're using, and then you sort of create this protocol object, which is then sort of a description of the scientific work you're about to do. And then finally, you can create a directed acyclic graph of computational work, which will then sort of perform an estimate for you. And then you can kind of run that sort of locally, or you can kind of more likely distribute it out to your HPC or cloud service. And so sort of the complete amount of code that it would take to run a free energy calculation using this framework is sort of given here. So that's not too many lines of code for what is quite a complex thing to do. So just to sort of drive home what all these different things actually talk about are, we've sort of defined this base layer, which is a common language by which things should talk to each other. There are various individual tools which are then talking in this language to each other and sort of fulfilling certain roles. And then we're kind of wrapping that up as the last stage into sort of final application, which is sort of maybe a user-friendly layer. If you just wanted to use stuff, you could arrive at that point and it's all sort of working together, but there's sort of been a lot of developer work in getting that to work. And we also have this available as a command line interface. If you really want something push button that maybe even a medicinal chemist could do, you know, that exists as well. So our sort of flagship first protocol that we've created is a protocol for relative free energies. We base this off of work out of John's lab using Perses. This is sort of built on a stack of OpenMM tools OpenMM feeding into OpenMM tools, feeding into Perses, and then we've got PyMBar as the estimator on the end of this. This is going to run you a relative free energy calculation with a hybrid topology. There's a choice of sample there, so you can use href, sans, or just independent lambda windows. That's everything I had to say there. And so we've gone and benchmarked this to sort of check that it's safe to use and it's going to work for you. And sort of these are the plots that we're getting out of this. This is again using open force field because why wouldn't you at this point? So these are absolute free energies that we've sort of derived using the maximum likelihood estimator, and we're seeing kind of these are genuinely quite good results. I think the plots which aren't looking so hot, like your MCL1s and your P38s, I think these are just known problem cases rather than looking too bad. This is obviously a subset of the protein benchmark. And then we've also performed a retrospective comparison against some results that we got from David Harm, which I think were originally done using PMX using OpenForce Field 2.0. So PMX is a quite well respected, quite well established method, and so we wanted to see how we would stack up against that. So on the left, you have a comparison of the delta G, so sort of the raw relative results, and then on the right is a comparison of the derived absolute values. And we're seeing, I think, that sort of we've got comparable accuracy. I don't think it's a lot better. I don't think it's a lot worse. I think there's some wins and some losses in there. But I think hopefully this provides confidence that this is something you could use that is as good as sort of other tools which are out there. So yeah, so I kind of get asked now and then about sort of what is open free energy. I think I've got two sort of stock answers depending on who I think I'm talking to. And it's kind of a bit of duality and a bit of double think going on. So some people, I think it's a collection of components which you could assemble for working with and performing free energy calculations. And I think some people, it is a complete end-to-end pipeline for those free energy calculations, depending on how you look at it. But I also think this isn't a binary thing. I think this is sort of a spectrum. I think you could start with a pipeline, but then start sort of pulling that apart and replacing components and sort of adjusting that workflow as you need it to sort of do more complicated things. I think some people sort of a single person who are sort of facing up against a team of medicinal chemists, and for that you might opt for the end-to-end pipeline, which is going to give you more throughput. I think there are other teams which are looking for sort of a technological advantage, and so for that you might start to view it as a collection of components that you can then, because this is all freely licensed, you can then sort of mix and match these with your own in-house code to produce something which is truly competitive with these sort of good building blocks to start with. So two different ways of looking at maybe the same thing. So that was all sort of in the present tense, sort of trying to stick to time. I try to only stick to sort of things which you could use today. So there's a lot of things which are in the works sort of coming out soon and in the future. This is our picture of our year 2 roadmap that I think we wrote up a while ago, but I think we're holding true to it quite well. So things we're currently working on are this sort of onboarding experience and sort of getting people using it, using the tools. We're going to be continually looking at sort of widening the domain of applicability and what you can do, looking at improving the accuracy of the existing relative free energy protocol. We've got an absolute binding free energy protocol in the works, which I think is probably done in a few months, 2 or 3 months maybe. We've got the Kartograf map that the bench has been working on, which I think is looking quite promising. That should be ready fairly soon. So if you're interested in sort of trying some comparisons between different mappers, that might be interesting to try. A lot of the free energy plots that everyone's been putting up have been using this sort of arsenic cinnabar tool, which is another example of a tool that we've adopted and sort of tried to help maintain and develop. It's one of those things that seems too important to fail, but at the same time, no one's taking care of it. So we're working on that. Currently, that's only sort of suitable for retrospective plotting, and I'm trying to sort of look at making that also good for prospective plotting. That's a bit of a what's the word? Not flaw in it. It doesn't do that currently anyway. Other thing we have going on is here. I've put everything. And these sort of purple boxes are collaborations that we have sort of going on with academic teams. So a lot of what I've spoke about is sort of stuff that the team is personally doing, but we're also working with various academic groups who are starting to sort of build software within this framework that, again, you can use as this sort of common interface. So you can switch in new protocols and new methods. So I think we have a non-equilibrium based approach coming out of John's lab soon, which is sort of Percy's non-equilibrium cycling approach that we're looking forward to use. Separated topologies might also be on the horizon, and we're looking at the networks that HiMap might create. So those are quite interesting and sort of an alternative to maybe more traditional Lomap based approaches in the sort of the topology of the free energy network. Am I doing the time? I've completely lost track. 20-ish. Okay, I'm good then. So tomorrow we have like a lot of discussions going on with the team. We're quite interested in talking to people about various topics around free energy, and I'd like to sort of just give a shout out to those so that people are aware they're going on. So tomorrow morning we have a hands-on sort of tutorial session where people can try this out for themselves, run some calculations, and sort of see how it would look and feel. And this is being followed up by user feedback sessions because we're quite keen to get feedback on how that went. So that's Sunday morning with David, but the whole team will be there for that. I think the importance of benchmarks has been sort of already stated, so I'm not going to sort of go over that too much, but I think they're a massive use to the community, and so we'd like to put a discussion on what future benchmarks could be run, how could these be different, and sort of how we can expand those, but also how can we maintain our existing benchmark sets so they stay relative and they're still useful in the future. So that's a talk that's just going on just before lunch on Sunday. I think I saw this sort of multi-stage approach to sort of looking at free energy calculations. Currently, we handle this sort of middle case of sort of mapping free energy methods and sort of the analysis of results. System parameterization is obviously open force fields thing. And you'll be coming in from various angles depending on how you're doing your system prep and your docking. And so we're kind of interested in what are your expectations for the tools as they come in, and what sort of outputs would you like to create? And also, so maybe question, what is the scope of the project, and should we move backwards, should we move forwards? Sort of what should the project do? Because that can be quite adaptive. There's a lot of really interesting methods which have come out. We've just been at the Free Energy Conference for the last few days. There's a lot of really fun new methods out there. We're holding a discussion on sort of what's hot and what's on the horizon, sort of what would people like to see and what are people curious about. That is a discussion which Irfan is holding tomorrow afternoon. And then finally, this topic of sort of atom mappings and planning networks is quite important to your results. If you get this wrong, then you'll waste a lot of computer time. So we're also going to have a chat about sort of strategies for this, what works, what doesn't work, and sort of what would people like to see more of and less of. And then finally, on the Monday, which is in 2 days' time, we're going to have a quick chat about workflow and data management, which I think is going to be riveting. But I think it's quite important. I think it's important that we're able to scale up our computational works. It's quite a dry topic, but I think there are a lot of solutions out there. We're going to hear about one in just a moment. But I think it's something which can save a lot of human time and sort of use resources available to us quite well. And so it'd be quite good to sort of hear from people, what are they using, what are they liking, what are they hating, sort of what's the current state of how people are running their work. So we're doing that one. Right, and with that, I've reached the end of my talk. I would like to sort of personally thank a lot of the people that have helped me sort of with this project. It's been a very ambitious and interesting project, and I've had a lot of good advice that I probably haven't followed as well as I could have, but I'd like to thank people anyway. I would like to thank our funders, Technical Advisory Committee that we benefit a lot from. We have quite good sort of working group going on with this ASAP project, which you're going to hear about in just a second. And I'd like to thank those guys. I'd like to thank the Open Force Field people for sort of making a lot of this possible. A lot of the shoulders were standing on the sort of listed there at the bottom. And I'd like to welcome questions and thank you. No questions, good.
Yeah, so we can take questions for a bit. He's under time, and other Jeff is going to be mic running, so make sure you have a mic before you start asking this question. That's fantastic. You asking me, they asked about energy, like when is it ready for me to actually put in labor on things that I have? You give an answer.
Yes.
Could you repeat the question for Tim?
Yes, the question was sort of, when can we use this? Is it ready for production use? I think the answer to that is yes. We're holding a session on that tomorrow with some sort of learning materials. These will be available online afterwards. Yes, with maybe it's a bit rocky currently. We're going to hear about that from Joe later, but I think it is ready for people to start engaging with, and that is maybe going to be important for how the project grows and goes forward, is sort of gathering that feedback, and we're going to be super appreciative of people that engage in that process, and we're willing to sort of support that as it goes. So conditioned yes, I think is what I gave there. Should I check the chat or not? No, that's fine.
Oh, question. What? It's a silly question. Oh, we got a mic for you.
Yeah, the Deathly Hallows logo. It's a now chemical symbol, so it's the project might have been called Open Alchemy a year ago, and I was sort of choosing between two names, and so I ended up going halfway and having sort of one name and one logo. So it's now Chemical Transmutation logo. If you want to do a bit of procrastination, do like a deep Wikipedia dive, you can start sort of reading through the folklore of alchemy and the various symbols involved. It's quite a fun way to spend an afternoon. You've not got a lot on, but that's what the logo is. So,
Question in the back.
Yeah, I saw that ADHD on your roadmap. You details
yeah, I'm going to get sort of, if I get this wrong, I think it is, we're picking up the old Yank code and sort of running with that. So it should be a ADFD, which is similar to how Yank works. So I'm not going to talk too much about the exact details of that because I don't want to get it wrong. But if you talk to Irfan later, he'll be able to sort of fill you in on that. So it will sort of be OpenMM based, absolute defining pre-entry protocol, which would be similar to what you could get out of Yank and OpenMM tools if you sort of managed to put those together yourself.